opposite of capacitors in terms of how they work. So what we see here is in this circuit above right here, so this is our circuit, we've got an EMF of 20 volts, it comes up, we hit a resistor of 10 ohms, and then there's a switch here that could go to A, or we could flip it to B. Across A, we've got a 15 microfarad capacitor, and then it comes down and goes back to the 20 ohm and then completes the circuit. Or if we're in B, we've got a 2 Henry inductor here in this other parallel branch. The capacitor is initially uncharged, which is nice for us, and a voltmeter, which is not shown, and we'll see why in a second, is used to measure the correct potential difference across resistor R1. So we'll see why it's not shown right now. In the diagram above, we need to draw the voltmeter with the proper connections for correctly measuring the potential difference across R1. So if we remember for a voltmeter, voltmeters are put in a parallel branch with whatever we're trying to measure. Unlike a amp meter, which is in a parallel branch because the current needs to flow through it, the voltmeter is actually going to sit out here. And remember, we put all of our instruments in kind of a little circle here, voltmeter. Doesn't matter that this piece of wire here connects at exactly that point. It could have in theory connected down here. There'd be nothing wrong with that. This wire is in theory a perfect conductor. We just need to go across the R1 branch there. So that was part A, that easy. We've correctly placed that. And we called it a voltmeter. At time 0, t equals 0, the switch is moved to position A. Okay, so let's just set this switch to A so that we have it. What is the voltmeter reading immediately after this switch is gone at time equals 0? Well, at this point, we're going across the capacitor. And at time equals 0, the capacitor, which is uncharged, is going to act as a wire. So this capacitor, we can imagine that it doesn't really exist. It's like not there. It's just a wire at this point. And if it's just a wire, then my entire circuit is just the 20 volt EMF, the 10 ohm R1 resistor, and then the 20 ohm resistor on the other end. So if I want to figure out how much EMF is going across that 10 ohm resistor there, we could find the current and then multiply it by the 10 ohm. If we actually were kind of clever about this, and we'll see this in a second, we could do a quick ratio. But looking at this, to find the total current, we need to find the equivalent resistor here, and since these are in series, we can just add them together, 10 plus 20 ohms to get 30. So this will be 20 over 30 equals the total current, and that will give us 2/3 or 0.66 amps. And that means if I just take, and I want to find the voltage across the 10 ohm, the voltage across the 10 ohm is equal to the current, 0.66 amps, times the resistor there of 10, which gives me that the voltage is 6.6 volts. And that's just Ohm's law, V equals IR. What we could have also done real quick is noticing that this is a very simple circuit with only 2 resistors. I know that of the 30 amps, or of the 30 ohms of resistance, this resistor is only taking 10 of it. It is supplying that 10 of the 30, or a third of it. So I know that this is going to have a third of the voltage drop, and this is going to have 2/3 of the voltage drop. So I could just take 20 over 3 and call it a day here. And if you do 20 divided by 3, you get 6.66 repeating as well. So that's a kind of quick way if you know what you're doing. This is the more proven way with Ohm's law. Now, after a long time, and a long time is like an infinite amount of time, because we know for a capacitor it never fully gets to its charge. But after a long time, so we can say pretty much infinity, the potential across R1 is taken again. So now, when the capacitor is fully charged, it actually acts as a break in the circuit. And if there's a break in the circuit, the current can't actually flow, and we're not going to see anything around this. So what we're going to have here is that the voltmeter reading across the R1 resistor here, well, that's still V equals IR of the 10 ohm resistor. The current here is 0 amps because the current's not flowing. It's a broken system because of that capacitor. And the resistance on it's 10, but who really cares, because 0 times 10 is 0. So we're not going to get any voltage across that resistor there because, well, the capacitor is fully charged. It acts as a broken wire in this case. We don't have anything there. To find the charge on the capacitor, though, the charge on the capacitor, Q, is equal to C, the capacitance of the capacitor, times the voltage across that capacitor as well. We know that that voltage across the capacitor, since it is fully charged by just a 20 volt EMF source, we know that that voltage is going to be equal. And it has to be equal because whatever this EMF of 20 volts is pushing, this capacitor, which acts as the broken wire because it's fully charged, this capacitor is pushing back with the same amount. So it needs to sit at 20 volts whenever it's charged. So we know the capacitance here is 15 microfarads. So that's times 10 to the minus 6th farads. And then we know the voltage here is 20 volts. So 15 times negative 6 times 20 gives us some number. And let's just work it out. 15 times 10 to the minus 6 times 20. 3 times 10 to the minus 4. And that answer is in coulombs because it is a charge. Woo! I guess if you wanted to, you could just do 15 times 20 and keep the micro, but whatever. This is fine as well. At a even later time, beyond the infinity, the switch has been moved. Ooh, we've gone to position B here. What's the voltmeter reading for this time at t equals this new 0 time? Okay, so let's see why this matters. Well, if we go back up here, at this new time, I don't care about the capacitor anymore, so whatever. But what has occurred is that we are now going across to our inductor. Okay, so we're coming around this way now, and we're going through the inductor at some new start of a circuit. Okay, I've completely ignored the capacitor. Who cares? It no longer matters. We can scribble it out. This is what we care about out here. Now, what we need to remember is the very instant that an inductor is starting to take current through it, it is acting in an opposite way as a capacitor would. So because we have this large change here, this inductor initially begins as a broken wire. And at a long time later, that inductor will act as just a regular wire with no resistance. So at the initial position of B, when that switch is gone, we essentially have a broken wire. And if we're looking for the voltmeter reading on the broken wire, we're actually going to have exactly what happened to this scenario for the fully charged capacitor. We're going to see the V10 equals 0 amps because it is a broken wire setup, because the inductor initially allows 0 current through it, times the 10 ohms, and that just equals 0 volts. A long time later, the inductor acts as just a wire. So if we're looking for the final current here, then in this case, all we need to do is we need to set up the system and pretend that that inductor hasn't really done anything. So if we set up the system, and I'll just redraw the circuit, there's 20 volts. There's our 10 ohm resistor we've been playing with the voltage probe across it. The inductor is just a wire now. It's just a wire. We're not worried about any of the weird stuff it does. We come back, there's the 20 ohm, and then boom. So if we just want to find the current through this setup, these are in series again, so we can just add them together. So with Ohm's law, V equals IR, which we've been using a lot in circuits, we can just say that the current, which is equal across everything, is equal to 20 volts divided by the sum of the resistances, which in series we're just adding them together, 10 plus 20. And that will equal the total current, which is the final current in this case, which just equals 20 over 30, which is 2/3 amps. Cool. We need to determine the final energy stored in the inductor. So to determine the energy of the inductor, we're looking for a stored energy here, so some sort of like potential, so to speak. And for an inductor, and this is sitting on the equation sheet if you don't remember it, because we don't use this equation all that often in the AP class, but it's very similar to kinetic energies, graphs in a very similar way. It's equal to 1/2, and if we think about kinetic energy, it's a 1/2 times an intrinsic quantity, the mass, times the velocity squared. For inductors, it's 1/2 times the intrinsic quantity, which is the inductance, L. And then our velocity we can think about here is actually the current. So it's going to be 1/2 Li squared. So it looks very similar, but it treats into electric form. Luckily for us, we have everything for this in this problem. The 1/2 is the 1/2. The inductance here was just 2 henries, kind of a weird unit, but is what it is. So there's our 2 henries, and then our current here was the 0.66, or the 2/3. So there's 2/3 amps, and don't forget that square. At this point, we can just multiply everything together. Kind of nice thing about this is the 2 and the half go away, and 2 squared is 4, and 3 squared is 9, so we quickly get an answer just of 4/9 joules, because joules have to be energy. So that's a quick one, didn't even need a calculator. Last but not least here, we've got a differential equation. We are writing it, but not solving it. And remember, anytime in a circuit problem, we are asked to write a differential equation, we should immediately start thinking about Kirchhoff loops. I'm missing an F there. Okay, we need to start thinking about looping structures. And we're looking for potential drops. So how does the voltage change across each of our setups here? And we're doing this for the current in the resistor as a function of time after the switch is moved to position B. So let's just quickly redraw our circuit so we have it. Redrawing circuits is super helpful. So there's the 10 ohm. Now we have the inductor here. We can't forget about it. And then here we've got the 20 ohm. Okay, and that inductor was 2 Henry. So it doesn't matter which direction we go around with our Kirchhoff loop. I'm going to go around clockwise here. Just why not? When I go around clockwise, and I can just arbitrarily pick a direction of the current. It doesn't matter which direction I pick, but I am going to pick that the current is in the same direction as my loop. This way, whenever I go across resistors, I'll be subtracting the potential instead of adding it back. When I do this then, I'm going across the EMF source from the negative to positive, which means I'm gaining it. This is irrespective of the direction of current you pick. All that matters is you went across it from a low to a high potential. So we've gained the EMF. And then when we go across, so that's the 20 there, that's the 20 volts. And then when we go across this 10 ohm resistor, the voltage across it is going to be the current times the resistance. So the voltage across it's going to be the current, whatever it is, I don't know what it is, times 10. Now, for this, because I'm going with the current in my loop, they're in the same direction, I'm going to lose this EMF, this voltage. So minus I times 10 ohms. When I continue moving along, I'm coming across this inductor. Now, we're technically trying to add all the pieces here, but if we remember the inductor, an EMF across an inductor is equal to the opposite, due to convention, of L, and this is where things get a little weird and why they're asking you to write a differential. It's di dt. Okay, and that's why we're writing but not solving this sucker, because they don't want to have us do an integral right now in a full-blown derivation. But this is what we want. We're adding up all the voltage drops here, so when we add the negative L di dt, what we get here is negative L di dt, and then we've got to go across our 20 ohm resistor, which, because we're going in the same direction as the current as it wraps around, is a minus I times 20 ohm. And then since we've come back to the very start where we began, according to Kirchhoff's loop, that equals 0. So that's our setup right there. If we wanted to, we could recognize that these are like terms and they can be put together. So we could, if we wanted to be like fully complete, say that this is 20 volts minus 30 ohms, that's the 10 and the 20, times I. And if we wanted to, we could move the L di dt to the other side. But that's not required. We're actually fine just leaving this equation like this because everything's there. So not too bad, and we're not even asked to integrate that or anything, which is very nice. If we were, we'd have to pull this entire left term over. It'd be kind of a pain, but we could do it. Nothing too bad. Okay, so there's a classic little RC RL circuit for us. The nice thing about this is there wasn't a lot of calculus in it. In fact, other than just writing the differential equation, there was no integration or derivatives there. But a lot of it was understanding what's going on with a circuit for both a capacitor and inductors for whenever time begins and at a long time later. So that's something we should definitely know this year, especially with the way the AP test is formatted for 2020, given the whole corona situation. I think you're going to see something like this pretty easily. Okay, but that's the problem. We are done with it. We are finished. You take it easy. Go check out some other videos. Stay safe out there. Adios.